Hi guys, in this video let's pick up with our discussion of acetals. In the previous video we showed synthesis of acetals from an aldehyde or ketone using either two equivalents of an alcohol or one equivalent of a diol. And if we use a diol, we will get a cyclic acetal because the two oxygens are connected via the original bonding between them. And we talked about the practical reason you might use a diol is that it has a higher boiling point than the water product. And so we can do this reaction at maybe 110 or 120 degrees and distill out the water as it's formed to drive the equilibrium, but we would not be distilling out the diol because it has a much higher boiling point. So a practical consideration there. So cyclic acetals are fairly common. But now we're ready to pick up with the idea of acetals as aldehyde or ketone protecting groups. And that's really one of the claim to fame for acetals. So, what if we had this difunctional compound here with the ester and the ketone? And what if we wanted to just reduce the ester? Now my X is sort of on top of this structure here, but the ketone has not reacted or been reduced, but it looks like LAH is reducing the ester to the alcohol. What if you wanted to make compound A? Well, you would not be able to do that by reacting this compound with LAH because LAH would react with both the ketone and ester. And in fact, the ketone is more electrophilic because the oxygen is a stronger donating group to this carbonyl because it donates by resonance. So the ketone is actually going to react more quickly with the hydride reagent as opposed to here we need the ester to react. Ultimately, LAH would reduce both carbonyls and we would end up with this diol here. Simple addition to the ketone and a simple addition elimination to the ester to give the aldehyde, and then it's further reduced by a simple addition. So how could we make compound A? Well, a common strategy here is to make an acetal of the ketone. React it with this diol, an acid catalyst, and that would give... Now please pause the video, please show the product here, and I can tell you this is only going to react with the ketone. Now you do have to be careful here. It could possibly react with the ester. That's reasonable to consider or question. Okay? But in practice, it's known that this type of molecule will react preferentially with the ketone here. And what we can get is the acetal here, and that would look like and there's 3 carbons linking these. And that is a 6-membered cyclic acetal. Okay. Plus water. Just to reiterate that, okay? The original oxygen is going to be lost as water as the other two oxygens attack that carbon. We've done mechanism above. Now we can come in here with our LAH. And it will only react with the ester because we only have one carbonyl now. The acetal is not electrophilic. Nucleophiles will not attack the acetal. Acetals are unreactive unless you're under acidic conditions. If you're under acidic conditions, which we were here, okay, this can go backwards back to the carbonyl compound. But what we can do here is we can reduce the ester, sort of a double reduction, and that would give that product there. The aldehyde is the intermediate again. For some reason I feel like you guys are not seeing how we get to here. Okay. Pretty straightforward. Addition, elimination, give aldehyde. Addition again. It's going to give this oxygen anion. And then we got to have workup. And workup is often not mentioned. Sometimes we can clarify that, but very often it's not shown, but it's implied. Okay, we get this product here. Now if we take this and treat this with H3O plus, we can hydrolyze the acetal back to the carbonyl compound, and this will release the in this case the diol. This is just the diol that we used here. Don't confuse this diol here with that diol there. Okay. Just the acetal going back to the carbonyl. We could come this way. You take the carbonyl, react it with the diol, we would come back this way, right? Okay. Going that way, we want to use aqueous acid with excess water, because water would drive the equilibrium back to the carbonyl side. Okay. So by using an acetal, by using an aldehyde or ketone protecting group, the acetal serves to protect the ketone, kind of mask it. Then we reduce the other group, then we deprotect and go back to the carbonyl. Now, acetals can also serve as diol protecting groups. If you look at this diphenol, if you tried to make a Grignard of it, it has this bromine here, oxidative addition of the magnesium. Okay? Because maybe you wanted to make this Grignard and then react it with an epoxide. Not going to work. Because as soon as you make this Grignard, you're just going to get a proton transfer. This is essentially a carbanion. It's going to take the acidic H of another molecule. Okay, and that carbon has taken an H, and you're going to end up with oxygen anions, depending on which oxygen it takes the H from. You cannot make a Grignard in the presence of an acidic H, like a protic solvent or even a protic functional group. All right, so you're never going to, the Grignard will not survive long enough to get the epoxide in there. All right. Well, actually what we could do here is we could react the diol with an aldehyde or ketone, and that would give our acetal. Okay? Right? Aldehyde or ketone, two equivalents of an OH, okay? Aldehyde or ketone, diol, all right? In this particular case, the diol is sort of our main compound. It's also it's also a diphenol, but it's still a diol. And that reaction would give this here plus water that carbon there used to be the carbonyl carbon of acetone. Please make sure you do this mechanism. I can easily see where this come from, but I suspect you guys cannot. That's okay. That's why I'm asking you to really make sure you can see how we're getting to here. This is an acetal that came from reacting with acetone. It's actually known as an acetonide. Okay, and on this page here, we had something very similar. That's why it's called the drug acetonide, where this is the regular drug. Now we can react this with magnesium, and there's no proton here. We can make a Grignard. Now we can react this with anything we want. The acetal survives, reacted there, then with H3O plus workup, we can just call it workup. That will protonate the oxygen, but it would also hydrolyze your acetal, and we would get that, and we would get back our acetone. Okay. So this is an example. See here, acetone was not our major organic substrate here. In this case, it was the diol. The acetone is going to go in the waste container, where up here, compound A was our main product, and the diol goes into the waste container. Of course, those can be recycled, but you get the point. The focus here was on the carbonyl compound, and the focus down here is on the diol. Acetals is drug. I showed one on the warm-up page. Okay. Structures of sugars. Some sweet chemistry. In the miscellaneous handout, one of the pages looks at carbohydrates. And carbohydrates are typically shown in two forms. A non-cyclic form, usually shown as Fischer projections, because a carbohydrate has multiple chiral carbons. But these can also cyclize, all right? And I've never noticed this before, but we are missing an OH group. Why is it missing there? Interesting. But this OH group, looks like I wrote that in too. Okay, I don't know where I got this from, but looks like there was a little bit of glitch with this. This OH comes around and attacks that carbonyl. It's showing it right here. Okay. Yeah, this had some problems here. They're missing H's here. Here's the oxygen. We just made this bond. And this carbon will end up with an OH after we do a proton transfer. And this OH can either be equatorial or axial. And that's what they're trying to show here. They didn't do a good job there. They left out the H. All right. Down below we see both forms. Here the OH is axial and here it is equatorial. All right. Now when it's axial and it is thus trans to that CH2OH group, that is known as alpha. These are also known as anomers. Okay. You can look that term up. That's called the alpha anomer, and when the OH is equatorial and thus cis to that CH2OH group, that's called the beta anomer. And the beta is actually favored largely because we know that the OH being in the equatorial position tends to be favored. There could be other considerations to why beta is favored. Okay, but these two forms are known as they're the alpha and beta anomeric forms. But these are hemiacetals. Okay, now we actually showed hemiacetal back over here, and I didn't mention it. But right here, okay, instead of this doing a proton transfer, if we had instead just lost the proton back to the catalyst, that would look like we'd have an OH and an O ethyl. Now I'm drawing both of those upwards, okay? OH and an O ethyl on that carbon. That is sort of halfway to the acetal. We've replaced, well, we haven't really replaced any oxygen yet, but we've got one alcohol on the carbon. All right? The acetal has the two alcohol groups on the carbon. This is known as a hemiacetal. All right? We haven't lost the water yet. By the way, it's also, some people refer to this as a half acetal. Kind of like that term. So that's what these really are. Okay? Hemiacetals. This carbon has the OR group, the alcohol group, but it also still has the OH. Hemiacetal, but we also have some stereochemistry here. That's some carbohydrate chemistry you will see in biochemistry. We also had, back in this example here with the amygdalin, that's actually an acetal because both O groups have ORs. There's no OH here. When the OH is there, it's called a hemiacetal. Okay. So some sweet chemistry there. Next, let's look at reactions of aldehydes and ketones with amines. Now this reaction gives a functional group. Okay, we need to know all these new functional groups. An imine. An imine is where the oxygen of the aldehyde ketone has been replaced with a nitrogen. And since the nitrogen is trivalent, it's going to have another bond. It can be to an H, or it can be to an R group. And it doesn't have to be carbon. We'll see an N to O type compound later. We also form water. These reactions are reversible. Okay, of course we're under Roman numeral we're under Roman numeral 2, and we're under B, additions with loss of water. So this is an addition of the amine with loss of water. All right. We can do this mechanism. Acid catalyst. First thing you want to do is protonate your carbonyl. I'm going to skip that step because I assume everyone can protonate a carbonyl. Then the nucleophilic amine. Add to the carbonyl, electrons up. Just a simple addition to the protonated carbonyl. Ultimately, that oxygen is going to be lost as water if we start it. Okay, there's only one oxygen up here, there, so now it has to be the water. How do you make oxygen a better leaving group? Protonate it. We have this positive nitrogen. It looks sort of like an acid. Would love to lose a proton and go neutral. Okay, H plus transfer. Yep, there's no charge here. Now we have protonated oxygen. Now these electrons can move in here and kick off the water. Let me straighten out my bond angles a little bit. We now have double bond to N, H, H, and we have a methyl and a propyl. Nitrogen is now positive again. We just formed water. I'll show that by saying minus H2O. And now something can take back the H. There's got to be a catalyst, an anion here. Maybe we used a little sulfuric acid and we have this oxygen anion takes the H, these electrons stay behind. That would give our imine with one H remaining, lone pair of course, and we would reform our sulfuric acid. We could use any strong acid here. Now, in some cases, the acid catalyst is not always needed. Okay. That's particularly the case if your imine, especially if imine is conjugated. And is thus has some stability, or is more stable than non-conjugated. Here we just have an isolated double bond. Okay, if we use methylamine, there'd be a methyl left because at this point there would be an H and a methyl. you're not going to lose the methyl. Something would take the H and you would deprotonate the nitrogen, leaving the methyl group. That's the only difference. Okay? I'll let you do these two for homework. Okay? I'm not showing an H plus catalyst here. You can, sometimes it's not shown. You pretty much have to know that a primary amine is going to react with an aldehyde or ketone to give an imine. Now you can also use ammonia. You would not call that a primary amine. Okay? Now secondary amines actually do not give imines. They can't. They give enamines. And it's the same mechanism as above, except you're going to get to okay, same exact mechanism using dimethylamine here or any other secondary amine. At this point, okay, you've got one H to lose, proton transfer, but no more. You'll be left with two methyls. There is not another H to lose here. All right. But you do lose an H. But instead of losing one from nitrogen, you lose one from an alpha carbon or an adjacent carbon. There's two H's here, there's only one H here. All right. Now, you can do this, show this mechanism all in one step, or we can first show resonance. This nitrogen is electronegative. Let's move these pi electrons here. I'm just going to call these methyl groups. Okay. True structure is a hybrid. But right here we can better envision the base, the weak base, okay? Taking this H and these electrons moving in, and that gives us our enamine. Now this looks a lot like the second step of an E1 elimination where we take a beta hydrogen. Okay, here I'm calling it a beta hydrogen. It's alpha to the carbon, it's beta to the nitrogen. Don't be confused by that. When we did elimination, we certainly, in doing an E1, we call this a beta hydrogen. Put in that double bond because there's no H to take from the nitrogen. And that's the result you get when you use a secondary amine. Okay? Ene, like an alkene amine. Enamine. Sort of like an enol if there was an alkene with an alcohol. Now with tertiary amines, you do not get any reaction. Okay? No reaction with tertiary amine. At least no kind of standard introductory reaction. There may be some fancy, peculiar reaction you get. There's always exceptions. But we're not going to show any reaction here because it's just nothing's typically obtained or no common reaction of an aldehyde or ketone with a tertiary amine. In terms of when the amine is acting as a nucleophile adding to the carbonyl. Okay. And by the way, sometimes you see enamines in drugs. If you look at this drug here, used to treat fibromyalgia. You see the enamine here. It's also got a primary amine, cyclopropane, benzene ring. Good looking molecule, yeah? You can look this up on Wikipedia for some information about the drug activity. Okay, now with imines, lots of application of imines. Okay, lots of application here of imines and enamines. All right. And one thing here is some kind of specialized imines. If you react an aldehyde or ketone with hydrazine, you will get an imine. One of the amino groups adds and you get an imine. But the imine will have a NH2 group bonded to the nitrogen. And that is called a hydrazone. It's a special type of imines, okay? Now, if you use hydroxylamine, the amino group will react and condense, okay? And you'll produce water, just as above. But the nitrogen will have the OH group bonded to it. That's just a special type of imine, but it's called an oxime. Maybe this comes from oxygen imine. This comes from the fact that a aldehyde or ketone reacted with hydrazine. Okay? All of these new functional groups you should know. Now, if you react an aldehyde or ketone with this hydrazine, it's a substituted hydrazine, you would expect to get, now the primary amine is what's going to react here. It's also more reactive, okay, because the other lone pair is conjugated with the ring. So you get the imine here, all right, but it's actually called a hydrazone. It's just the hydrazone has a group on the second nitrogen. It is a 2,4-dinitrophenyl hydrazone. But this reaction is used as a chemical test to determine the presence of aldehydes or ketones. Okay? And particularly when they are, well, not always, but usually when these are liquids and you add this hydrazine in a solution in ethanol, and this reaction takes place pretty quickly, and you get a yellow-orange precipitate of the 2,4-DNP, 2,4-diphenyl hydrazone. And the precipitate indicates that you had an aldehyde or ketone. All right. No reaction with acid derivatives, such as an ester or an amide. Now, it would react with an acid chloride. So there are some particulars to how this can be used as a test. This is kind of a little bit vague here. It will react with an acid chloride. Now, These are also used as derivatives. For example, this ketone would be a liquid. You can make the 2,4-DNP derivative, and now you can obtain a melting point. And the melting point of the derivative can help you determine what aldehyde or ketone you may have had, if that information is known. And you can actually look up in books, it'll have aldehyde or ketones, just listed. And then it'll have over here, it'll say the melting point of DNP derivative. And for this aldehyde ketone, maybe the melting point was 122 to 124. For this one, it was 167 to 168. Okay, like this. This one was 201 to 202. And so the idea here, you think, well, I think I have an aldehyde ketone. I think it's one of these. And, I got lots of data. Well, one more thing I could do is I could make the DNP derivative of this and get the melting point of that. And say you do that, and your melting point turns out to be, right about 123. You say, hey, well, that's further evidence that I must have had that aldehyde or ketone. That type of thing was especially done a while back, 50, 100 years ago, before they had as much, or before we had as much analytical capabilities, such as NMR, etc. Okay, but it can also be used as a quick chemical test. Next, Wolff-Kishner reduction, something we've seen before. And now we can take a look at the mechanism for this. All right, removing the oxygen. All right. And why don't we pick up there in the next video? But I'll give you a little hint. The first step is converting this to the hydrazone. From there we will continue on with hydroxide. I will also tell you this reaction forms nitrogen gas. Structure, of course, N triple bond N. Thus, we want to get triple bonds between the nitrogen. If you want to give this a try, the first step is deprotonating this nitrogen, doing resonance structures. Keep in mind, we want to get two H's on the carbon. It's really just a series of removing H's, doing resonance, and putting them back on carbon. But eventually we're going to have to kick off that carbon, and that's when we generate the nitrogen. You might give it a try on your own. We'll pick up here in the next video. After that, we will also continue with amines, okay? All right. Lots of application of amines.